Welcome to the deep dive. Today, we're pulling back the curtain on an incredible hidden world. Think about the phone in your hand, the laptop you're using, maybe even the smart devices around your home. Beneath those sleek surfaces, there are tiny components, intricate layers, and just a mind boggling amount of engineering. But what happens when problems lurk beneath that surface? Invisible to the naked eye, threatening to derail all that incredible tech. That's precisely what we're diving into today. An innovative solution called 3D near infrared tomography, or NIR tomography for short. This isn't just about seeing things, it's really about seeing through things, specifically in that incredibly precise world of semiconductor manufacturing and advanced packaging.
Right. And our mission for this deep dive really is to unpack exactly how this cutting-edge tech tackles some of the most critical challenges facing the industry right now. We're talking about feature sizes shrinking down to the nanometer scale. That makes defects unbelievably hard to spot. Then there's the increasing complexity of 2.5D and 3D integration. Think of it like building a skyscraper of tiny computer chips, stacking them up. This creates really complex structures like through silicon vias, TSVs, through glass vias, TGVs, tiny bumps, multi-layer designs, all notoriously difficult to inspect properly. And add to that the demand for ultra-high yield, even the tiniest flaw, minuscule, can lead to massive financial losses. Traditional inspection methods, they often just look at the surface.
Right, skin deep.
Yeah, exactly. But the real problems, the tricky ones, they often hide beneath, unseen, until, bam, they cause these costly yield busts.
So it sounds like these hidden flaws are a huge threat to, well, the devices we rely on every day. How is this revolutionary 3D NIR technology actually able to find them? What's the magic? What lets it see through all those layers?
That's a great question. It really comes down to the unique properties of near-infrared light itself. We're talking specific wavelengths here, typically ranging from 900 to about 1700 nanometers.
Okay, and what's special about that particular spectrum of light? I mean, why not just use a really powerful flashlight or visible light?
Well, what's fascinating here is how NIR light behaves so differently from the light we see. Unlike visible light, NIR has significantly lower scattering and lower absorption when it passes through common semiconductor materials, things like silicon, glass, polymers. And this unique property, that's precisely what allows it to penetrate hundreds of microns, sometimes even up to millimeters. It gives you this unprecedented view beneath the surface of these incredibly intricate components. It's almost like X-ray vision for microchips, but using light.
Wow, so it's not just a simple point and shoot then. How does it turn that light penetration into like a detailed 3D image? Is it just one angle?
Oh, definitely more complex than that.
Hmm.
Systems like the one developed by Junhao and Opixeon, they use a sophisticated imaging technique. It involves multi-angle scanning and then 3D reconstruction. They use multi-angle illumination, basically shining light from various directions to capture different perspectives, to get the full picture. And the system captures both reflected light, which is great for surface details and shallow features, and also transmitted light. That's what reveals the deeper hidden structures. All this data then gets fed into these complex computational imaging algorithms, and they reconstruct a true 3D model. So you get both lateral resolution, that's your X and Y axis across the surface, and crucially, that critical depth information, the Z-axis, see into the layers. Conceptually, yeah, it's a bit similar to optical coherence tomography, OCT, maybe you've heard of that, but it's specifically adapted for semiconductor materials and processes.
And the level of detail sounds astounding. You mentioned micron level resolution. Can you help us picture that? Just how precise is it? And what kind of problems does that suddenly make visible?
It means we can detect incredibly small issues. We're talking tiny cracks you'd never see otherwise, voids, little bubbles or gaps and abnormalities within those vital through silicon vias.
Those vertical highways through the chip.
Exactly. Connecting different layers. We can see inside tiny bumps too, and even check the integrity of the layered interfaces. These are the kinds of issues that could easily cause a device to fail later on, but now they're detectable much earlier.
Okay, but even with NIR getting through the material, you mentioned light scattering. Doesn't that distort the image, make things blurry, especially deep down? How does 3D NIR overcome that? That seems like a pretty significant hurdle if you want clear images from deep inside.
That's a crucial point, absolutely. And it's where a lot of the real innovation comes in. It uses a combination of sophisticated techniques to tackle scattering and recover that image clarity. First off, there's optimal wavelength selection. By using the NIR2 region, that's 1,000 to 1,700 nanometers, it offers even lower scattering in silicon and polymers. Think of it like finding the perfect radio frequency to cut through static, reduces signal loss, improves penetration depth.
Got it. Fine-tuning the light.
Precisely. Then uniform illumination and multi-angle acquisition are key. Uniform light prevents, hot spots or dark areas. Consistent quality. And like we said, multi-angle scanning captures diverse signal paths. This helps compensate for scattering effects, any blind spots you might get from just one angle. It builds a more complete data set.
Okay, so multiple angles help fill in the gaps caused by scattering.
Exactly. Third, they use techniques like wavefront shaping or phase modulation. These are pretty advanced. They actively correct the phase distortions caused by scattering. Imagine looking through like a funhouse mirror. Wavefront shaping detects that distortion and then reshapes the light to counteract it.
Ah.
Yeah, it lets the system refocus light precisely onto those subsurface structures, pulling out image clarity that would otherwise be lost in the blur.
That's like giving the light smart glasses, basically.
Sort of. And finally, there's the power of AI-powered descattering algorithms.
AI, of course.
Artificial intelligence models play a vital role here. Think of them as super smart noise cancellation for images. They're trained to extract meaningful features from what looks like noisy, scattered signals. Filtering out the static, machine learning then helps enhance the reconstruction of those deep layer images, turning chaos into clarity, giving engineers a really unprecedented look inside.
It really sounds like a multi-pronged attack on that blurriness, transforming guesswork into, well, precise insight. So we've talked about the magic, how it sees through things, how it overcomes the challenges. Let's shift gears a bit. Where are engineers actually putting this to work right now? What practical problems is it solving that, impact the reliability of the devices you, the listener, use every day?
Okay, yeah, let's get practical. A big one, and one that often flies under the radar, is scribe street chipping inspection. Scribe streets, they're those really narrow regions where the silicon wafer gets diced into individual chips. It's basically the cutting zone. Now, during that dicing process, tiny chips or microcracks can happen. And critically, sometimes they extend beyond the scribe street right into the active parts of the chip. This can cause electrical leakage, mechanical weakness, or just outright reliability failures later in the product's life.
So before 3D NIR, manufacturers were kind of flying blind on these hidden cracks, hoping for the best, maybe facing costly recalls later, like finding a tiny crack in your car's frame after you drove it off the lot.
That's a good analogy. Exactly. Traditionally, inspecting this meant destructive physical cross-sectioning, literally breaking the wafer apart to look inside.
Ouch. Costly.
Very. And visual methods, just not good enough for those hidden subsurface cracks. 3D NIR solves this. It penetrates the silicon or the local dielectric layers, reveals hidden cracks, delamination along interfaces. It prevents those latent failures in packaged devices, improves yield significantly. Another crucial one, post-TGV laser drilling inspection. TGV means through glass via. After lasers drill these tiny holes through glass layers, manufacturers need to check the via dimensions, make sure the walls are smooth, again, traditionally. Destructive cross-sectioning. 3D NIR gives you a non-destructive way to visualize those internal via structures, look for residue, microcracks.
And what about after they fill those vias? I imagine a tiny air bubble or a gap in the metal filling could be disastrous.
Absolutely. That brings us right to post-metallization inspection. After filling TSVs or bumps with metal, you can get defects like voids or delamination where the metal pulls away. 3D NIR can non-destructively check if those vias are fully filled, if there are any internal cracks or gaps. It's like an internal quality check without breaking anything open. And in advanced packaging like 2.5D and 3D stacking. Multi-layer stack packaging inspection is huge. The more layers you stack, the harder it gets to inspect. 3D NIR reveals crucial details, the interfaces between layers, how accurately the chips are aligned, any delamination or voids between those layers. Super important for these complex chip skyscrapers. And finally, it's just invaluable for real-time debugging. Engineers can use 3D NIR to rapidly find and analyze internal defects during manufacturing. That significantly cuts downtime, prevents costly yield loss right there on the line, saves potentially millions.
These capabilities really are transforming quality control, aren't they? And efficiency, too. It sounds like it's not just about finding flaws, but maybe enabling the next generation of complex devices that maybe couldn't be built reliably without this kind of X-ray vision. It's fundamentally shaping future tech.
You've really hit on a core insight there. It's more than just a better inspection tool. It's an enabler for innovation. And when you compare 3D NIR to other common techniques, like, say, visible light, automated optical inspection, AOI, or even X-ray, 3D NIR really offers some distinct advantages. Its ability to non-destructively image deep inside materials, that micron-level 3D resolution, the AI-driven defect recognition, its versatility across different processes, it truly sets it apart.
And I guess it aligns perfectly with where the whole semiconductor industry is heading. What are the big trends where 3D NIR is likely to play a major role?
Oh, absolutely. It aligns perfectly with the biggest trends. We're seeing continued growth in heterogeneous integration, advanced packaging, all demanding more sophisticated deep inspection. Then there's the constant shrinking of feature sizes, pushing defects down into the nanometer realm, even harder to find. And finally, the rise of smart manufacturing. AI-driven real-time defect detection is becoming standard, moving from reactive fixes to proactive prevention. 3D NIR fits right into that.
And it's exciting to think about how 3D NIR itself might evolve. What's next for the technology?
Yeah, the roadmap looks interesting. Moving towards real-time inline process monitoring, getting that feedback instantly during production. Integration with other methods like X-ray, OCT, maybe hyperspectral imaging for even more comprehensive insights. A multi-tool approach. And the deeper integration of big data and AI for predictive maintenance, using the data to anticipate problems before they even happen. So if we connect this all back to the bigger picture, Junhao Precision and Opison Technologies' 3D NIR scanner, it fundamentally solves that problem of invisible defects, those hidden flaws inside chips and packages, including critical issues like that scribe street chipping we talked about, which, often quietly threatens the reliability of the final product. It really shifts quality control from just finding bad parts to actively preventing them from being made in the first place.
And that makes it an absolutely critical enabler for improving yield, optimizing processes, and ultimately significant cost reduction in advanced semiconductor manufacturing. So the next time you pick up your phone or use your computer or interact with any smart device, just take a second. Consider that invisible world humming away beneath its surface. Technologies like 3D NIR, they aren't just finding flaws, they're fundamentally building a future where the devices we rely on every single day are more robust, more efficient, and ultimately more dependable than ever before. Which maybe raises an interesting question for you. How many more invisible challenges like this are being tackled behind the scenes every day in the technologies that make your digital life work so seamlessly?